Modeling degradation. That's the final part of our fourth lecture, closing chapter 5. So we're going to be talking in this part mainly about section 5.5 of our book. Let me write it here. Section 5.5 of DIP 4th edition, because things start to get interesting. The maths is start to get more involving. So I do recommend you to read this section. If you don't have time to read the whole chapter, read this section to understand it better. So basically, what we're going to be doing in this part of the lecture, we're going to be studying ways to estimate the degradation operator. Recalling that the image that you get is assumed to be the result of the original image convolved by a degradation operator summed by a noise portion. This H is also called the blurry function, even though some of these degradations are not blurring the image, it's doing something else, but it's well known, usually known as blurry function. And I do recommend this Coursera course here. I built my lectures trying to make the lectures better than what this guy does. One can only try, right? He is very good, and I've learned a lot watching his lectures. And in particular, this part, I do recommend you to watch his explanation about modeling degradation. Okay, so let's assume that we have no noise. So this term goes away, and we end up with only this part of the noise modeling. Now, if we take the Fourier transform, we end up in the frequency space where a convolution becomes a multiplication. This is explained in the chapter that I skipped. So if you want to know the derivation coming from here to that, read, I think it's chapter 4 of the book. Let me just make sure. Yep, chapter 4. So if we have an estimate for the degradation function on the frequency domain, I can obtain the original image. I can reconstruct the image by just getting the resulting image, the image that resulted from the degradation process, right? This is G function, and just divide that by the by your degradation estimate. Of course, you can divide. You can use simply division, because here you are on the frequency domain. This is frequency domain. This is not spatial domain. And then in the end, once you get that, you go back. So you do an inverse Fourier transform, and you go back to the spatial domain and have your image totally reconstructed. Now, having an estimate of your degradation, you can just divide it. And if we manage to estimate the future, what we have to do is take the observed image, apply a Fourier transform the estimated future, divide one by the other, get your image on the your reconstructed image, and then you go back to the spatial domain and you have your function reconstructed. That's, in a nutshell, this is what it's called inverse futuring. It's a quite powerful technique for image restoration. Well, then there is a question: how can we estimate H? How can you estimate your degradation function? Well, of course, there are very complex procedures for that. we're going to discuss a few of them, but it's difficult, but not impossible. One simple example is that you apply a well-known impulse, a well-known signal to your imaging device, such as, in this case, an impulse of light. And then you check the answer of your imaging device. So you're gonna get some sort of blurred dot or with some other degradation here. So you use this blurred dot to get the parameters of a Gaussian. And you assume that this Gaussian is your degradation operator, that you're gonna apply convolve this Gaussian to the original image to get the degraded image. That's easy peasy. Once you have that, you do this whole process that is explained here, right? So if you know that this is a Gaussian degradation, and we know that the original image is a dot, we can estimate the parameters of the Gaussian, and we can use this to calibrate the system and reconstruct your images. So imagine if you get an image of a faraway galaxy that's all blurred out. What can you do to reconstruct it? This, right? This. Okay. And you can have more difficult models, such as the model of turbulence. That you have very well, turbulence is what I get whenever I try to take a picture. When you shake your camera, that's the model of turbulence. It also can be modeled by a Gaussian filter, by a Gaussian degradation. Of course, the process of getting your turbulence model is a little bit more complex, but it's doable. Let's say the model of the estimation of a degradation function from a moving camera. It is a kind of turbulence model. Of course, if you, depending on the sort of the origin of your turbulence, it may get a little bit more pushy to do. So once you get this is the kind of pictures that I get when I try to photograph anything. I get this kind of blurred. This is the effect of a motion, right? When you move your camera, and instead of picking up one image, one single image, we pick up a sum of image. So your resulting photograph is actually an integral of various photographs during the space of time that you took for the shutter to close. Right? So by applying the Fourier transform, we get a filter with respect to the velocities involved in this linear motion. And then from the sum of multiple images, we can estimate one by applying an inverse filtering. Now, there are three ways to estimate the degradation function, either by observation or by experimentation or by mathematical modeling. Estimation by observation, we look, the idea is to look for a small section of the image that has a strong signal content. The index XS here is for a small section, and then construct a degradation of this section by using the sample intensities of the image at that point, right? If we get from a small section, you can get easily, well, easy is a matter of perspective. You can easily build your Gaussian model and divide it by the portion of the image at that particular section, and then you have your degradation operator. Now, if once you have this built from a small section of your image, you can generalize it for the whole image, creating a degradation operator on a large scale, but having the same shape, the same mathematical shape. Okay. Now, or the thing that we've just done, we try to obtain an impulse response of the degradation by imaging an impulse, small dot of light, using the system, and we model your Gaussian using the system, using the output, and you know that your image is an impulse. So you have it as input to the system. This is the easiest way, but sometimes you don't have these probing images that you can use to probe your system, and then you have to go for a small section of your pictures, and the same in a similar sense to what we've discussed in a previous video. All right, let's go a little bit further about the estimation by modeling. Estimation by modeling. You can model your linear motion, right? So you know that this so far. Oh, okay. So this estimation by observation is the stuff that we do. That you observe a small section. That's estimating by observation. Estimating by experimentation. You make experiments with your imaging device by inputting a well-known image and then analyzing the answer, and then finally estimating by modeling. When you make a mathematical model of your degradation, of the degradation that you get. So, for instance, assume that we have this kind of motion, this kind of movement, right? That's the kind of picture that I take all the time. Okay. So the kind of picture that I take all the time, you know that's a linear motion, and you get that's the result of a sum of an integral of various pictures taken at an interval of time, right? So I can apply a Fourier transform, getting this kind of motion where this is the Fourier transform of my motion, and this is the linear motion. The linear motion, I have a portion of the motion in t and a portion. Let's assume it's assuming that's a binary motion, right? A bidimensional motion in x and y. And this motion is your degradation model, right? So this portion here is the degradation operator that in the Fourier space, in the frequency domain, it's just a multiplication. It's just a multiplying factor on your original image. Okay, let's get rid of all of this. Right, so I can assume that Newton laws are respected when I take pictures. Well, when I take pictures, I'm not sure if I respect any laws of physics. But usually we do, right? Where the motion is the acceleration times t over the interval of time, right? That's the Newtonian physics. And let's assume that we only have movement in one dimension, only on x, just to facilitate matters, so where movement in y is 0. Now, this equation here for the degradation becomes this, where the integral is easy to calculate. It ends up on a very simple, well-behaved sinusoidal function. Right? Now, given this function, I can apply that on the original image, and get a resulting image, right? So if I model it correctly, multiplying this function with the original function on the Fourier domain, I'll get an output function, and if I turn this output function to the spatial domain, I should get exactly the same effect, or at least close enough to the pictures that I've taken with my camera myself. So, okay, so I modeled mathematically the degradation function. I found a mathematical model of the degradation function, and then with this mathematical model, I apply the same process that we discussed before for inverse filtering, right? Inverse filtering. Let me get rid of this. Take the observed image, apply a Fourier transform, apply Fourier transform of the estimated filter. What is the estimated filter? That's my mathematical modeling on the previous slide. Divide one by the other, get back at the image domain, and you have your image reconstructed. Clear enough? Good. Now, let's move on to our final filter. That is a Wiener filtering. It's a more advanced method for inverse filtering. The main idea is to minimize the mean square error between the reconstruction and the original signal. So this is the mean square error between the original signal and the reconstructed. That's the other way around. That's the reconstructed and that's the original. But we don't have the original function. We don't have the original function. Now f is not known. But we see that this is an expectation. It's an expectation. It's not the whole signal. So we can obtain that. We don't need the whole signal. We just need some statistical characterization of the original signal. The book on section 5.5 does all of the mathematical derivation for the Wiener filtering, which is quite nice, but it's we can take for granted that you can just apply this formally, and this represents the whole Wiener filtering, where your reconstructed image is the conjugate of your filtering divided by it's the conjugate of the degradation divided by the square of the degradation. This all on the frequency domain plus a term k that is derived from the statistics of the image multiplied by your degraded image, right? If you apply this, you're gonna get a very nice reconstructed image. So where h star is the complex conjugate of h, that's the function that produced the degradation. It could be a Gaussian, a motion, and this should be estimated. Estimated in the same ways that we discussed before, either by observation, by modeling, or by experimentation. The square of a degradation operator is just the conjugate multiplied by the original function, by the function in the frequency domain. K is a constant based on the statistical characterization of noise in the graded image. The book has a good derivation, but also this Wikipedia page, last time I've seen, is quite good. I recommend. It's very well explained. And Widmer filter is just, well, it's just in very hand waving way. It's just the solution to the least squares estimate, but in the frequency domain. And that's the result. Getting a corrupted image by some sort of turbulence. By applying inverse filtering, let's contrast inverse filtering with the Wiener filtering. Look, this is in the scale of reduced noise variance. So there's a great noise variance here, greater than here, With great noise variance with inverse filtering, I get nothing. Whereas with Wiener filtering, I sort of can see some stuff. I can read it. I can read that. Digital image processing. I can't see Master Yoda here. Now with reduced noise variance, with inverse filtering I can't still see, and now I can start to figure out Master Yoda here, and I can definitely read digital image processing. With good with very reduced noise variance. In this case, inverse filtering is good, but there is still some noise here. And now I can see, okay, and with linear filtering, this is a good image, and I can see, oh, how full I was. That was a Master Yoda. There was a flower here, a rose. And that's all for this week. So next week, next lecture, we're going to be talking about image processing with color images. Cool. I'll see you there. Thank you.